In this screencast, I'm going to kind of circle back and explain why we're interested in power of a test. And this relates to choice of sample size, how big of a sample you need to take in order to get a certain power. And I'm going to show you how we can use these operating characteristic curves. In one of the previous screencasts, I talked about power and beta. In those screencasts, I kind of had this assumption. I said, if the mean has shifted, then we can calculate a beta and we can calculate a power. And some of you might have been wondering, well, how do you know what the shift in mean is and why is that important? This is important from an industrial perspective. If the mean shifts, we want to be able to detect it. A lot of times you're performing quality assurance tests or assays, and over time, the mean of a product, whether that's purity or thickness or composition, can shift one way or the other. You want to be able to detect this shift in mean if it occurs. The probability of successfully detecting that the mean has shifted, what is that known as? That's right, the power of a test is the probability that you will correctly identify that the mean has shifted. In other words, you correctly accept the alternate hypothesis when in fact it is true. Let's go through an example of why we might be interested in a shift in mean. A batch chemical process produces a liquid product every 8 hours. The product yield varies from batch to batch, but is supposed to meet a specification of 95%. So 95% is your target. Based on a long history of batches, the yield adheres to a normal distribution and has a standard deviation of 1.4%. Now, this is the important part. If the mean yield drops to 94%, the process needs to be shut down and corrective measures must be taken. And so this shift in mean from 95% to 94%, that's a shift in mean, is really important. And if that happens, then the company needs to shut the process down and make corrective actions. So the question arises, in order to detect this 1% decrease in yield, how many batches would be required to do that? You can never do this with 100% certainty, so the power of this test, or the probability that you can successfully detect that 1% change, we're going to choose to be 90% here, so the power is 90%. And we're also going to assume a type 1 error risk of 5%. So that's kind of the example that we're going to be solving in this screencast. I think you all would agree that it's going to be much easier to identify a larger shift in mean, as shown on the right, as opposed to a smaller shift in mean. And that's exactly true. You want to somehow separate these two distributions, your hypothesized or your null distribution from the actual distribution. Your goal, after all, is to maximize the power and minimize beta. There are two ways to do this. One, you could increase alpha. Increasing alpha would bring that critical sample average over to the right for this lower-tailed test, and that would tend to decrease beta and increase power. However, this is a bad idea because as you increase alpha, you also increase the probability that you will accept the alternate hypothesis when in fact it is false. So you want to try to minimize alpha while simultaneously minimizing beta and increasing the power of the test. Another way to do this is to increase the sample size, increase n. Remember, these are sampling distributions, so if you increase n, you're going to narrow the distribution. In both of these diagrams on the left and right, the means of the null and alternate hypotheses are the same, but on the right, we are narrowing the distributions and we can dramatically increase the power while retaining the same alpha. So how do we determine the number of samples that should be taken? Let's talk first about the variance known case. Your book goes through the derivation of this equation, but you can calculate the number of samples that you need to take in order to detect a shift in mean of delta with a risk level alpha and a type 2 error of beta. The second option is somewhat outdated, and that's to use the operating characteristic curves in the back of your book. In the OC curves, you calculate this parameter D, which is just the absolute value of the shift in mean divided by the population standard deviation. So it essentially tells you how many standard deviations away from the mean you want to be able to detect. The OC curves are found in the back of your book. There's a bunch of them, and they all have different parameters. For example, this one is alpha equals 0.05. You can always tell the alpha because if you look at 0 for D, this approaches 1 minus alpha, and so that's 0.95. What we've got on the x-axis is the D, so that's our shift in mean divided by sigma. That's the number of standard deviations away from the mean that we want to be able to detect. And on the y-axis, this is the probability of accepting the null hypothesis when the alternate hypothesis is true. So this is beta. That's our type 2 error. So for example, if we had a power of 90%, that means we have beta of 0.1. And if we wanted to be able to detect one standard deviation away from the mean, we would need about 9 samples. There's all sorts of OC curves in the back of your book. Some are for the normal distribution, some are for the t-distribution. Here's another example for a different level of significance of 0.01. Let's go through and solve this example. We can use this equation. We can calculate z alpha and z beta using Excel or the tables in the back of your book. We square this, multiply it by our standard deviation squared, and then we divide by delta. Delta in our case is 94 minus 95. That's negative 1. I converted it to a positive number here, but really that should be negative 1 squared, but it doesn't really matter here. And what we end up getting is about 17 samples. So we need 17 samples in order to successfully detect a change from 95 to 94 90% of the time. We can also use the OC curves. We calculate this parameter D. Our mean shift, the absolute value of the mean shift is 1. So 1% divided by the standard deviation of 1.4. So our D is about 0.7. We can go in here. This is for alpha equals 0.05. D is 0.7. Power is 90%. So beta is 10%. That's, again, beta is shown on the y-axis. And if we do that, we end up with about the same result as we got with the numerical formula. We get about 17 to 18 samples.